Imagine a board game where you can move a piece along many different squares. White box testing is like looking at the whole board, not just the final score, and making sure every possible route the piece can take works correctly. A path is one complete route from the start of the program to its end, and a loop is a part of the route that can be walked around many times like a circular track. Testing these paths and loops is necessary because hidden bugs often live in rare routes that a user might only hit once in a while. If we only test the most common routes, we may miss those hidden problems, just like a driver who never checks the backroads might miss a pothole that could cause an accident later. A control flow graph, CFG, is like a city map that shows every street, statement, and every intersection decision point in a program. To build it, we start with the first line of code as the entry node. Whenever the code makes a choice, and if statement, a switch, etc., we draw a branch that leads to two new nodes, one for the true path, one for the false path. Loops are drawn as arrows that go back to an earlier node. The result is a picture where each node is a block of code, and each directed arrow shows where the program can go next. This visual map helps testers see all possible routes without actually running the program. Cyclomatic complexity tells us how many independent routes exist in a program. V of g equals e minus n plus 2p, where e is the number of edges, which are arrows in the control flow graph, n is the number of nodes, which are blocks, and p is the number of connected components, usually one for a single function. For example, a small function with 10 edges, 8 nodes, and one component gives v of g equals 10 minus 8 plus 2 times 1 equals 4. This number is the minimum amount of test cases needed to cover every independent path at least once. It acts like a route budget that guides us in picking which paths to test. A basis set of paths is the smallest collection of routes that, when combined, can represent every possible route through the program. Think of it like a set of shortcuts that let you visit every street in a city without needing to drive every possible combination of streets. To find it, we start with the CFG and select paths that each add a new edge not covered before. The number of paths in the basis set equals the cyclomatic complexity V of g. For instance, if V of g equals 3, we might pick 3 paths, one that goes straight through, one that takes the first if branch, and one that takes the second if branch. Testing these 3 paths guarantees that every edge in the graph has been exercised at least once. Loops can be tricky, like a playground carousel that you can ride 0 times once or many times. To be safe, we test 3 situations 0 iteration. The loop never runs like a door that stays closed single iteration. The loop runs exactly once, like stepping onto the carousel, and stepping off right away, and multiple iteration. The loop runs more than once, like riding the carousel for a full spin. By checking these 3 cases, we catch errors, such as off by 1 bugs, infinite loops, or wrong initialization, that only appear when the loop behaves differently. Mathematically, a program's feasible paths are the different ways you can travel from the start node to the exit node, without breaking the rules of the control flow graph. If a function has b binary branches, if statements, and L loops, the total number of raw paths is 2 to the b power times possible loop traversals. However, many of those paths are not independent, they share edges. The cyclomatic number V of g counts the independent ones. For loops, we often treat each loop as adding 1 extra independent path, the decision to enter or skip the loop. So a function with 2 if statements and 1 loop has V of g equals 2 plus 1 equals 4 independent paths. The extra plus 1 comes from the entry-exit structure. This enumeration helps us understand why exhaustive testing quickly becomes impossible for large programs. Explanation: to turn a path or loop coverage rule into actual test cases, we write concrete input values that force the program to travel the desired route. For example, if a path requires the condition x greater than 0 to be true and y equals 10 to be false, we choose x equals 5 and y equals 9. For loop coverage, we pick inputs that make the loop count 0, often an empty list, 1 a list with a single element, and many a list with several elements. Each test case is a recipe given these inputs. When the program runs, then, it should follow this path and produce the expected output. Writing the test case this way makes it easy to see which coverage criterion it satisfies. In the real world, we cannot test every possible path because the number grows exponentially with each new decision and loop. Exhaustive path loop coverage would take forever and cost too much. Just like trying to drive every possible route in a huge city would be impractical. Therefore, testers make trade-offs. They aim for the basis set, minimum independent paths, add extra tests for high-risk code, and use heuristics such as test the most common user flows first. Some limitations are hidden paths may still be missed. The CFG may be inaccurate for dynamic language features, and cyclomatic complexity does not capture data flow bugs. Knowing these limits helps teams balance thoroughness with practicality.